So what did we do on Tuesday? So we built this. I mean, actually, I have over here also this code that we went through. I'm not going to flip through the whole thing again. It's going to give you like vertigo. But we created this model carefully by putting together very expressive kernels that model different components of this data set. In fact, you could treat them as a causal interpretation, a causal description of what happens in this data set. And so one of these kernels models the periodic component, one models a long-term trend, one models a medium-term trend, one models very local weather patterns over the sensor, over this volcano in Hawaii. What have I missed? There's one more term probably that I forgot about. And with every one of these kernels that we introduced, that we added and multiplied together, we entered new parameters into our model. So that at the end, we now have actually, where are they defined? Here, we have something like, I keep saying 12, I haven't actually counted, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 parameters that we had to set to some value. So setting one of these parameters to a concrete value amounts to an assumption, a prior assumption, a modeling assumption. And initially, we did this with these deliberately round values that are just set to some like basic, orders of magnitude, multiples of 10 or sometimes 2 or 5. And then that already produced a plot that looked reasonably well, you could say. In particular, one way to assess a quality of a model visually, if you have two-dimensional data like this, or one-dimensional data, is to draw samples from the prior, and then we can check whether the data looks qualitatively different than samples from the model. In this case, you could argue it's quite a decent model, but if you kind of know the data, you might still see which one it is. Actually, can you visually? It's a bit tricky. Yeah, so we have asked you before. I think it is actually this curve here that goes all the way up. It's a little bit more regular than the others. So to make this model even better, we have to choose parameters that fit the data particularly well. Parameters that make this model produce samples that look more like the data. And the general framework for doing so is marginal likelihood optimization. This is actually still the exact same thing that we've been doing so far, namely Bayesian inference. It's not a new concept. It's just Bayesian inference on one more level of abstraction. So we are computing, in this case, not the posterior over the function that we want to predict, but we are marginalizing out this function that we don't know and want to infer to get a probability distribution for the data as a function of only the model parameters by integrating it out. And that is a likelihood, right? It's a likelihood term, a probability distribution for data given something we don't know, the parameters theta. And the only problem we have now is a computational one. It's that this likelihood is not of an easy algebraic form. By imposing our Gaussian process model assumptions onto this likelihood, and here, and this prior, we're arriving at a marginal likelihood for the model parameters that is fundamentally, it's not a Gaussian term containing a linear transformation of the parameters theta. But we can actually evaluate this likelihood. It looks like, this integral is closed form, so the likelihood looks like this. The predictive distribution for the data under the model is the prior mean of the model at the data points, and a Gaussian with the prior mean of the model as a mean, and a covariance that is given by the data covariance. And in general, all of these will depend on these unknown parameters theta. So if we wanted to do full Bayesian inference, just to be clear, we can write down what we would need to do. We would need to multiply by a prior here for theta, a p of theta, and then divide by this sort of meta evidence, which is the integral over this complicated likelihood times our prior, whichever one we would like to choose, integrated against theta. But because the relationships are so complicated, this integral will be very expensive. And at some point, we just have to sort of take a decision to say, now we've spent enough time, right? At least after 90 minutes of lecture, you should say, no, we don't want to invest more time into getting a better description of the data. And this is chiefly like our own laziness, right? So if you wanted to write a huge scientific paper about this model, then maybe you want to spend 2 more weeks thinking about how to build a better posterior here to get to quantify your uncertainty over the parameters. But what I did here was sort of a specific choice to at some point say, this is the highest level of abstraction we want to get to. If you wanted to do more, by the way, you'll typically end up introducing even more parameters. So for example, we could put a prior here over theta, and then that prior will be a choice we have to make. We'll impose what we know about theta. So as we keep doing that, our descriptions will become more and more abstract and will become more and more flexible in our modeling assumptions, but we'll also have to invest more and more computational resources. So the choice we now make is to do the sort of statistical approach and say, let's just find the mode of this marginal likelihood. Just a best guess, basically. That best guess we can find by maximizing this likelihood, which is the same as maximizing the logarithm of this likelihood, which is the same as minimizing minus the logarithm of the likelihood, because these are just, so the logarithm is a monotonic transformation. It doesn't change the location of the mode. Putting a minus and exchanging max and min doesn't do anything. It's just more convenient for optimizers. And then we can explicitly look at what these terms look like. I did this on Thursday. And we'll get an error term that basically just measures how far the data is from the prediction on the scale of how much volume the model distributes. And then an extra term, which comes from the fact that we've marginalized out the Gaussian distribution, that happens to be the determinant or log determinant of the the observation covariance, the covariance of y. And this is known as the Occam factor or the complexity factor. Why? Because it penalizes models that have a lot of flexibility. And so I could wave my hand around a bit and talk about the philosophical interpretations of this, which I did on Tuesday. But I also showed you this plot, which maybe we can now spend 2 more minutes on to think about what's happening here. This is a 2-dimensional intuitive motivation for why we are doing this and why this model complexity term should show up. What's actually happening when we are optimizing these parameters is that we're moving and scaling the probability distribution with the goal of putting as much mass as possible onto the measurements that we've made. So in this plot, I've boiled this down to a 1-dimensional example. Let's say I observed 1 sample from a Gaussian distribution, and I know what its mean is. The mean is here in the middle. I just don't know what the standard deviation is. Then I can try out possible different standard deviations. Here are 4 different candidates, basically. And so now the cool thing is that probability theory forces me to, well, use probabilities, so to distribute a finite amount of truth over this space, which means that when I make the parameters, when I make the distribution wide, when I increase standard deviation, then the distribution also becomes flatter. It doesn't just become broader, but it also has to, like, the y values have to come down, right? And as a result of this, there is actually an optimal value of sigma, and I can't just make the model as broad as possible to get a high probability distribution. And that's what this Occam factor actually does. So here in this plot over here, where I've plotted the value of these blue curves as a function of theta at the value z, you can see that there is actually a mode, a best choice, which happens to be exactly such that z is at 1 standard deviation. This is sort of a property of Gaussians. And this arises, the fact that this function has this sort of, it actually comes back down again, comes from this penalty term. So here I've plotted these 2 terms that show up in our loss function. The green thing is this square error, and this yellow thing here is this corresponding thing to the Occam factor, basically, but plotted in exponential space without the logarithm. And you can see that they sort of fight with each other, right? So to make this term look good, you want large standard deviation, because then you can explain large deviations from the prediction. But then you'll have to pay a higher price in model complexity, because you can explain anything. And that's this sort of philosophical interpretation. If you have a model that can explain anything, well, then that's not necessarily a good model, right? You want a model that explains only the thing you got to see. Yes. And so on Tuesday, someone actually asked, so what does this have to do with cross-validation? Does it have anything to do with cross-validation? Or maybe you suggested another thing we could do is cross-validation, right? So the statistical approach to model fitting that you also use often in deep learning or more generally statistical machine learning is to just try out different models. But then the idea is that you only train them on a subset of the data. You hold out some other part of the training data as a test set or a validation set to be precise, and then check how well these various choices of models work on the validation set. Now, it turns out that this approach is actually a weaker version of what we do here. There is a theorem that was interestingly only really phrased a few years ago, even though it's relatively straightforward to say that. Without wanting to diminish the contribution of Fong and Holmes. This is a paper that you can also read yourself if you click up here that contains a theorem that basically says marginal likelihood maximization, what we are doing here in our experiment, this is actually sort of an average over all possible cross-validation experiments you could make. So more precisely, their theorem says, imagine you have a data set, lots of y's, and you're doing cross-validation. That means you're maximizing a score that looks like this. This is called the cross-validation score. So what do we see here? Well, it's a very complicated formula, but it actually expresses something very simple. It says, imagine you have n data points. You're going to take p of these data points and turn them into a test set. Let's call that y tilde. And then what you're going to do is you're going to train your model on the rest of the data set. That's your that's your training set. And then you'll compute some kind of measure of quality, a score, of your model on the test set using the training set to train the model. And you'll do that for p data points that you've left out. And now you can do that for, well, if you leave p data points out, then there is n choose p possible ways of picking such a test set, right? So your cross-validation score is to do all these different permutations of these leave p out sets. That's what this fancy sum up here does in the front. So now the theorem says that the marginal likelihood of the model that the Bayesian model that underpins this prediction here is equal to the average leave p out score. So it's equal to actually, summing over all possible values of p, then dividing by n and multiplying by n, which is you just multiply the average score by n, which doesn't really change anything if you're picking the best model, right? It's just a constant multiple, where we choose the score to be the log predictive probability, which is what we did in our experiment, right? And so you can even try and do this proof for yourself. Just intuitively, the idea behind that is that if you have a exchangeable model, so if you have a likelihood for every individual datum that enters in a product over the model parameters, then you can probably imagine that if you take the logarithm of that, you get a sum, and then you can rearrange the terms in this product or in the sum in arbitrary fashions, right? Because the sum is commutative and the product is as well. And so you can actually do partial integrals over this, partially pick subparts of the data set and write this sum as a product all the way up to n minus p over the probability of y from y tilde n to p given y up to n. That's your training process, right? And you have a predictive distribution up to the test set times a remaining product from n minus p to n over the probability with a theta here, of course, for the remaining. Oh, it's the wrong way around. Yeah, so n minus p to n, but yeah, okay, you know what, yeah, I guess you sort of have an intuition for what I'm talking about, right? You basically split up the process into first predicting the training set, learning on that, marginalizing over it to get a likelihood for theta, and then what you're left with is the test set. But the trick is that you can do this in arbitrary orders because the model contains a product in the likelihood, and so you can rearrange in whichever way you like, and so the order doesn't actually matter. This is actually a general statement. It doesn't need Gaussian models. It just needs exchangeable models, so the likelihood has to be a product. But for those of you wondering where this determinant comes from, you might remember for yourself from your first-year undergraduate lectures, linear algebra, that determinants are these interesting objects that measure volume. And one way to define a matrix determinant is as a sum over all possible permutations of n columns and rows of a matrix. That's the symmetric group with n entries. Of the sign of the permutation times a product over all the columns of the matrix and where they are mapped to under this permutation. So the determinant contains this weird combinatorial structure already, and that's kind of what's reflecting this sort of polynomial term in the cross-validation here. You're checking for all possible ways in which you could rearrange the data set, basically. Now, this was all fancy math. What this boils down to for us is we can build a loss function that is just the log marginal probability distribution for the data under the model. And because we have our cool Gaussian class, we can just evaluate this log probability distribution like this. That's a question. Because it's in the loss function. There. Right? So there is a determinant there, and the determinant is this combinatorial object. That's all I'm saying, right? Really just, if you're wondering why there is a determinant, because a determinant measures volume under all possible permutations. Okay, and now, so we have a loss function, and that we can feed to an optimizer. And that, because you've probably all taken the deep learning class, is probably not surprising to you, right? And now we can hand this, like, we can just choose whichever optimizer you like. So here, we are, also if you like this connection, we're now doing something basically like deep learning. It's just that we fit a very unusual type of feature set, right? We're fitting entire probability distributions over function spaces rather than fitting individual parameters. But there's still a fitting process. And for that, we could call whichever optimizer we like. In deep learning, we've become accustomed to using stochastic optimizers for very large data sets. Here, we have a small data set with 800 data points, and so there's no noise. And therefore, it's much better, actually, to use a powerful numerical optimizer for smooth objectives. Also, this objective only has 11 dimensions, so it's not high dimensional. We don't have to worry about that at all. And we can compute its gradient and its Hessian, as you can see in this piece of code. And so I do this in the code. I'm not going to run it again because last time we had to wait 5 minutes to see it converge. This is the cell that does this. It's literally copied and pasted from the slide. It runs and it finds a value of 217, which is just a log probability. So it doesn't mean anything, but it's a low number. That's good. Then I made this plot that you've seen. I sort of made a little plotting thing, like printing tool that nicely arranges all these strings and tells us these are the parameters you started with. This is my little, poor man's weights and biases, right? I'm just like plotting results. These are the ones that the optimizer found. And then someone else did, like Carl Rasmussen, did the same experiment with the same model with a slightly different data set, and they arrived at these predictions. And then this is a good sanity check. We can convince ourselves that many of these numbers are very similar, but then some are very different. And annoyingly, the ones that are most different are the ones that we care about most, which are the ones that determine the behavior of the prediction far into the future. So what that actually means, let me go back again to our slides, is that maybe I was a bit over optimistic when I said, let's just do a point estimate. Because now we suddenly begin to question whether we should actually trust this point estimate. Right, so what we're doing here is we're fitting one single choice of theta And then we found such a single choice of theta. And now someone else gave us a different single choice of theta. And we're saying, oh, well, that's a different choice. What should I think about these two different estimates? So what we realize is that we need uncertainty after all. Now, conveniently, we already have the object we need in principle to do Bayesian inference, namely a likelihood. I mean, of course, we could also come up with a prior, by the way, for theta, right? So maybe just to be clear, it's absolutely trivial to turn this entire problem from a maximum likelihood to a maximum a posteriori estimate. We just add a log prior. For example, I could put some Gaussian prior over theta, right? It's just an 11-dimensional distribution, doesn't matter. But I don't want to because it's an 11-dimensional distribution, and I'm relatively certain that it has actually a well-defined mode. It's just that around this mode, in some directions, this likelihood is pretty broad, so it admits a lot of different choices of theta. And then along some other directions, it is very narrow, and so there's a lot of constraints. I actually tried to highlight this by making, so here are first of all the predictions again. To highlight this, and this was a bit quick on Thursday, by making a plot of the Hessian matrix of this loss function at these 2 points, at the one optimum that we found, that's the one on the right, and the one optimum that Carl Rasmussen found, which is the one on the left. I've actually clipped here the color scale, because otherwise, actually, do I want to try this and break my code again? So let me see what happens if I comment out. The see if that works. Yeah, so you can see that actually these Hessian matrices are completely dominated by these bits down here. Right, so this is where most of the curvature actually is. Now we get a huge color scale here. So remember these parameters down here. I could have, I mean, if I had more time, I could put a nice little axis labels here with all the different names of the parameters. I didn't. You'll remember that these are the ones for the short time scale models. These are the parameters for the weather patterns and their ranges, which have pretty small values. So they are in the range of 0.2 and so on. So what bites us here a little bit is that we're talking about physical quantities that have units of measure. And they have different units of measure, right? Some are in ppms, some are in years, some are dimensionless. And so it's perhaps not surprising that we get very varying, like relative and absolute curvature for these different dimensions. But nevertheless, even if I put in the scale again, the two dimensions at the top of the matrix, this region here, which determines the length scale and the output scale of the long-term trend, are extremely low curvature. So what does it mean if a likelihood has low curvature? That means it's flat along this direction, which means we don't know what the optimal value is. We could move around in the likelihood space, and the likelihood would barely change, right? We could move around in parameter space, and the likelihood would barely change. And so maybe, actually, both of these predictions here are pretty good. To get a sense for how good they are, what we can do is we can treat the log likelihood approximately as a Gaussian. And I'll not explain too much more how this works, because we'll have in like 1 or 2 lectures later on in the course about this. This is another Laplace approximation, another one like the one we briefly entertained in your homework exercise. No, not yet, but we briefly entertained it in lecture number 2 or 3, which is that what we're doing is we'll take the Hessian, so this matrix on the right, we'll invert it, because inverse curvature is like a covariance, right? If you have high curvature, then you're confident, so you have high precision, low variance. And if you have low curvature, then you're uncertain, you have high variance. So we invert it, and here we can actually call an inverse because it's 11-dimensional, it's going to be fine. take the diagonal of that matrix, take its square root. So the diagonal gives us a variance. You take a square root that gives us a standard deviation. And then we can, again, print that and print these standard deviations next to the numbers. And now we see that these numbers actually have huge error bars, which easily include the predictions from the other measurement. Curvature of the, okay, let me maybe go through a slide that, well, yeah, I'm talking about the curvature of this function at the point theta that the optimizer found as a function of theta. So the second derivative of this function with respect to the entries in theta. Because this is a likelihood for theta, so if this were a Gaussian, which it isn't, then that curvature would be constant, and its inverse would be the variance of that Gaussian. That's the match. Okay. So the takeaway from this is, even when you do hyperparameter optimization with maximum likelihood, you may still care about an error bar on that maximum likelihood estimate. And because we're now in a regime where we can't do full Bayesian inference anymore, it may be useful to use something approximate to get a sense for how uncertain you are. Later on in the course, I'll bring up other ways of being approximately uncertain about stuff. Right? So far, we've mostly dealt with the Gaussian mechanism where everything is analytic. Now we have, for the first time, maybe a situation where we have a proper non-Gaussian distribution. And I've highlighted one very crude ad hoc way, which actually also happens to be a very general, powerful framework, Laplace approximations, to get an error bar nevertheless. And now, so what's left maybe for you, if you want to play with this data set, and you will kind of have to for your homework anyway, is to try out how the predictions of this model change if you move around in this space a little bit. So, by the way, one way to do that, like in a very concrete way, is you can build a Gaussian over theta, over the parameters, with its mean set to the choice of the optimizer. So this is called results.x in this cell. And the covariance set to exactly this. That's it. And you can call that Gaussian and have it draw for you 5 different choices of theta. That'll be 5 different 11-dimensional vectors. And for each of these choices, you can make one of these plots. Just see how different the models look. OK. And now there's a final thing I want to do that I kind of have to show you now because it's also on the homework exercise, which is to finish this story of our experimental analysis of this Keeling curve. Namely, let me go back, to motivate this, let me go back to this plot. So what we did here is we built this complicated model that contains all these different kernels. It's now, I think, 5 different kernels with 11 parameters. And they are summed up to describe what's happening in this data set. Actually, 2 of them are multiplied together with each other, and then the other ones are summed up. And that gives us a joint prediction of what will happen next. But we motivated this model by saying adding kernels together, which is like OR interactions, hopefully. I always get it confused. Amounts to saying that there are different terms interacting with each other in an additive fashion. So I had a plot that, or a slide that looked like this, that says you can think of individual functions, f1, f2, that together make up this data set, and we add them all together to get the actual observations that we get. So now a question you might ask at the end is, well, what do the individual functions actually look like that make up the sum? There's this additive model. What are the components of this? Now, conveniently, because sums are linear maps, and Gaussians are closed under linear maps, we can also do the reverse projection and take the sum of the functions, which are the observations that we've made, and project back out into the original space of the individual functions. To do that, we, instead of, so so to get to the data from the function space, so let's say we have two functions, we get to the space in which we make observations by summing those two functions. If we have something that lives in a space of y's, that's exactly wrong. We need to project out by the transpose of this operation, not this one, but the transpose out, so the 1, 1 vector, and then we get predictions for the individual functions. And we can just do that because Gaussians are closed under linear maps, right? Now, this map, 1, 1 transpose, is not the inverse of a matrix, right? Because it's not a matrix that is invertible, but it doesn't matter. It's still a linear map that maps back into the space of the individual functions. This process is called source separation, oops, and we can just do it. So for that, the only little computational trick is that we need the ability to take Gaussian processes and project them through a linear map, which so far we hadn't implemented yet for Gaussian processes. So I actually do this in our Gaussian class. I implemented a method called project. I recommend that you have a look. It's already in the class, so you can just check it out. It's pretty straightforward. It just does the projection on the mean and the covariance matrix. I mean, it basically implements this operation here, where we just put a b on the left and right, and you just come up with the projection operator. Oops, what's going on here? And then I make a plot that projects onto the individual terms in our model. First, I project onto the first two components, which are the long-term trend and the medium-term trend. And I'm plotting both of them. So each of these projections is itself a Gaussian process, because linear projections of Gaussian processes are Gaussian processes. And so I can draw from them. I can use all the methods that this class has. I do this here. And in red, so in blue you see the data. In red you see the long-term trend prediction. And in green, on a different y-axis, you see the medium-term trend. It's on a different y-axis because it's so small, and its theta output scale value is so small that you would otherwise not see it. Yeah, so what you're supposed to see here is that these are both Gaussian processes, so we can draw samples from them, and they have interesting structure. And also, perhaps interestingly, the variance reacts in an interesting way. So even though we are actually quite confident about the prediction of the joint model, so let me go back up here, right? Remember that the error bars here are very small, so the model is very confident about what happens here. When we look at the individual components, the predictive error is actually larger. And that's just linear algebra working, basically. Intuitively, right, if I have a Gaussian model with two objects and I know a lot about their linear projection along some line, then I can be quite confident along that direction and yet still be quite uncertain along either of the original axes. Right? That's what's happening here, just in a higher dimensional space. So, but nevertheless, we see that there's a long-term trend, and with this choice of parameters, it doesn't look like it's abating anytime soon. So we should be very worried about these numbers because, as I said, around 500, we know that there will be at least cognitive effects on humans, let alone on nature and the planet around us. But then again, maybe there's a little bit of hope because, as I said, this data still allows us actually also choices of much shorter length scales for this long-term trend. So maybe we're lucky and humanity as a whole becomes smarter and kind of gets this curve bent down. We can also do the same thing for the other kernels. So in your homework, I've also asked you to make, or we have asked you to make a plot of some other parts of the prediction. Maybe the most fun one to look at, because it's a different kind of projection, is this periodic kernel. So remember that we have also this kernel in there that models the seasonal component of the data set coming up and down, and it's multiplied with this square exponential kernel that allows this component to drift over time. And so we can make a prediction for what this periodic component will look like as a function of time. And that's what I make in this cell. I'm not going to go through how I actually make these plots. You can look at them yourself. So because it's a periodic component, it makes no sense to plot it over the entire time axis, but instead I'm plotting it over the circle, basically. You could also think of some kind of polar coordinate plot if you like, but I'm just going to make the prediction with a heat map like this. So on the x-axis, you see the month of the year. This is a periodic function, so it gets blue over there and then continues blue and so on. So what you see is that in the second half of the year, there is a negative component from plants extracting CO2, and then in the first half of the year, a positive component from sort of overshoot, if you like. And then I'm plotting, because this is a term that can drift over time, I'm plotting it for every year in the data set, from the 60s all the way into the future. And now what you can see is that this model predicts ever so slightly a shift of the seasons towards earlier in the year, right? Now, and so if we believe this model, and of course we can immediately come up with explanations, right? We can sort of say, spring comes earlier in the northern hemisphere. We see this ourselves. There's all these data sets that support this, like in Japan, the spring cherry blossom comes earlier every year, right? So this is kind of maybe what we see here, that this white line has a small trend towards the left. But then again, to be more confident about this kind of statement, what would we need to do? Well, we need to check how much our model actually supports alternative hypotheses. So for example, if you do what I suggested, you draw other theta values from a Gaussian approximate over the parameter space, and then keep doing that, these plots, like just make many of these plots, then you'll see, maybe, I haven't done it, try it out, maybe you'll see different dynamic behavior in the seasons. Maybe there's even some hypotheses that suggest that the seasons don't change. I don't know. Okay, are there any questions about this first half of the recap, analysis of the stuff we did on Tuesday? Yes? So you mean why we are uncertain about it or how we are quantifying it? So we're uncertain about it because this data set does not uniquely identify one choice of thetas. Say again? No, so there isn't necessarily more than one mode of this distribution, but the mode of a distribution is not the entire distribution, right? So if a probability distribution looks like this, then this is the mode, but that still doesn't mean that that's the right answer, right? The correct answer could be here, or there, or anywhere else. So just the mode itself is not necessarily a good object. In fact, the mode is a particularly bad object because it transforms non-trivially under changes of variable, right? So if I would take this space and just say, instead of that space, I want to take the exponential of this variable or the logarithm of that variable, it's still the same variable. It's just a different way of looking at the data, but then the mode will shift. It'll be in a completely different point. So it's not necessarily a good estimate. It's just sort of one typical point within the data, within the possible choices. It's maybe an interesting one to look at because it's easy to find with a numerical optimizer, but it's not the uniquely correct one. So what we're doing is we're finding the curvature at that point, or actually the log curvature. So the exponential of that gives us something Gaussian, and you can use that as a local approximation to the distribution. Yes? This particular optimizer that I'm calling, this Newton CG, only works on continuous parameters. That's a good point to point out. If you have a model class where you also make discrete choices, an example of that would be you don't know whether you want to include one of these kernels or not, right? You could say, is there a medium-term trend or not? That's a discrete choice. Then you need a mixed integer program optimization routine. It's still the same quantity we're optimizing. It's now, you just need now an optimizer that can deal with discrete choices. So in scipy.optimize, there are also MIPS, mixed integer program solvers. These are less efficient, or I mean, in a way they're more powerful, but the task is much harder. You may remember from your theory of CS class that discrete optimization problems can be very hard indeed, including NP-complete problems. So that while the likelihood is the right framework to describe that we could have such choices, by allowing ourselves to consider an arbitrary countable space of other options, we're also posing a much harder problem to the optimizer and to ourselves. Okay, now then this is also exactly the right time to take a break, and we'll be back in 5 minutes with something else. Now we can get to the content that I actually wanted to do today, which I'll now only do very quickly. And I'll skip maybe through a few things and leave them maybe to Marvin, who is doing next week's exercise sheet and then the tutorial after that. Because he was supposed to be here actually to give this entire lecture today. And then he went to a conference in Southeast Asia, and despite all the, I don't know, 12 vaccinations that he got, he still caught some nasty flu somewhere in Seoul. And so he can't quite make it here today, and that's why I'm back here and tell you about how to optimize hyperparameters. So this lecture is supposed to be the bookends to the chapter in the course about Gaussian regression in particular. Gaussians are not gone yet. They're going to stay with us for the entire rest of the term as a tool, not as the focus of our attention now. From next Tuesday, we'll talk about another model class, in particular, first of all, time series and sequential data, and then after about 2 or 3 weeks, more general distributions about general types of data, and then learning representations, deep learning, probabilistic approximations to deep learning, and then finally, maybe sections on randomness, samples, and various types of other approximate inference techniques, like mixture type models, ideas of connections to attention, and so on. But today, I want to wrap up a little bit of the math for this, which are maybe questions that some of you may have had over the last 2 weeks in particular, as we've been talking about Gaussian process models, kernel machines, because this is basically the entire part on kernel machines. So after this lecture, we'll not talk about kernel machines anymore, at least not concretely in their instantiation as kernel machines, as Gaussian process models. And I realized, so to do that, I need to do a little bit of math. So I do this type of lecture every time I teach this class. And every year it gets a bit shorter, a bit more compact, and I realized that it's not for everyone. After this, I usually get feedback by people saying, well, that was too much math, I didn't understand it. Let me see how well I can do this term. If you're already worried about the exam, there are going to be some things I'll say here that are relevant for the exam, but if there's some stuff in there that feels like totally over the top, don't worry about it, it's not going to be in the exam. If you want to read up more about this, there's a lot of deep math books for those of you who like to read books that are like where the cover is just one color and there's just words on them and no picture, and when you open up it's just math, then I recommend any of these. In particular, Ingo Steinwart's book is amazing in that regard. Here in the middle, the pointer is gone, doesn't matter, like up here. And also this paper, which is very detailed. And the goal of this is to make a connection, and this is also why we're doing all of this today, to what you may hear, well, actually what you used to hear in the statistical machine learning class. So it used to be that the stats ML class, when machine learning had a more civilized age, was a lot about functional analysis and kernel machines and the spaces that they explore, and function spaces, functional analysis. And then there was this probabilistic machine learning class that talked about stochastic processes and Gaussian processes in particular, and so on. And there was always a question of how these two actually fit together. Also socially, there were actually 2 different communities. There were the statistical machine learning people and the Bayesians, if you like. And those 2 communities, they didn't really mix. So that's also why we have these 2 different lectures. With these few slides, I want to try and make a connection between them. So first of all, maybe let's start naively. Me having introduced Gaussian process models, in the way that I did. I started with parametric regression, so that we can learn functions by choosing particular features that map from inputs to outputs, putting weights on these features, and then learning those weights. Then I said, oh, actually, when we do that, we can do some kind of functional representation of this process in a lazy way that doesn't instantiate the features, and that amounts to a Gaussian process. In fact, when we do that, we get this kernel object in the middle of our computation, and we can actually sometimes get away with this kernel object, which is an inner sum between features, being an implicit sum over features, where we don't actually instantiate the features, we just do give the sum in there sufficient structure that it becomes analytic without having to instantiate the features. And then it's possible to sometimes deal with infinitely many features. We did several of these constructions for the square exponential kernel, for the Matern kernel and their entire family, and the Wiener process, and the integrated Wiener process, and so on. When I did that, you might have said, these kernels, these functions that take two inputs and return numbers, and we use them to populate matrices, how should I think about them? What are they? Are they matrices? Are they functions? What are they? Well, so one first intuition is that kernels are a little bit like infinite dimensional matrices. And to do that, let me just quickly recap what a matrix is, right? So the finite dimensional object, the one that you encounter in your linear algebra class, if you take a first year undergraduate linear algebra class, are these linear maps A, explicit linear maps, that take vectors, which are finite objects, and map them onto another finite object, another vector. And they do that by doing these inner products, right? Where we take a product between the matrix and the vector by summing over elements, like this, right? This is the movement that you do in your head. And then you learn that there's this beautiful theory, maybe one of the most foundational theories of mathematics, that shows that such matrices can be described by characteristic objects that are sometimes called eigenvalues, and matrices can be described by particular vectors which have the property that when you multiply the matrix by the vector, you actually just scale that vector rather than transforming it into some other vector. And there's a theorem that connects these vectors to the matrices themselves and says the space spanned by these matrices is actually spanned by these specific vectors called the eigenvectors, scaled by the eigenvalues. And that defines a representation of the matrix like this. There's also a special matrix, 1, by the way, which has the property that when you map it, apply it to any vector, you just get back the vector. And yeah, so that's maybe obvious, but actually we'll come back to it in a second. So now it turns out, and here I just have to tell you that that's the fact, that's the case, because this is not a functional analysis class, that there's a corresponding concept for kernels. Namely, just like there are vectors for matrices, specific vectors that have the property that they don't change under the application of the matrix, except for a scaling, there are functions for kernels that have the specific property that when you map them through the kernel, and then mapping here has to involve an integral because it's a function, right? So it's infinite dimensional as an object. You get back the same function scaled by just a number. And these functions are called eigenfunctions. And their theory is associated with this guy here, James Mercer, English mathematician. And there is a corresponding theorem, Mercer's theorem, to the one on the previous slide, that says just like you can write a matrix as being generated by its eigenvectors, you can write any positive definite function, any kernel, as being generated by its eigenfunctions. So when we write this notation k indexed by AB, this stuff that I used across all of these different slides, k AB, or k training set, test set, training set. This is really a little bit like going something like this. right? We're indexing in some kind of infinite dimensional space, if you like. There's a bit of a caveat, though, namely that these eigenfunctions, as you saw on the previous slide, are defined by integrals. And integrals are infinite sums. And when you do an infinite sum, you have to say how you do the sum. For discrete sums, there is only one way to do the sum, right? Because there's just finitely many elements, and you have to sum them all up. But when you take a space that is continuous, and you want to define a sum operation on it, an integral, you need to put a measure over the space. You'll remember from lecture 2, measures are a bit tricky. You can pick measures in different ways. And so this definition is relative to a measure over the space. And actually, those functions look different depending on that measure. So they are only relative to how you measure over the space. OK. And the other problem is that for a general positive definite function, a kernel, it's not always straightforward to find out what the eigenfunctions are. For some kernels, under some specific base measures, they are known. For example, for the square exponential kernel, the eigenfunctions are known. But for more general kernels, they're not known. So this is just an analytic tool, not something we can make universal use of. A little bit of use, though. For example, there is one cool trick to make kernel machines faster computationally for specific kernels, like the square exponential kernel, that uses a projection onto their leading eigenfunctions in a very specific way. This is sometimes called, these are called spectral methods or random feature expansions, or sometimes also kitchen sinks. OK, so that was takeaway number 1. Yes, Gaussian process models are really operating on infinite dimensional spaces that are somehow spanned by these kernels. And this span is explicitly, or maybe, like you can really think of some space created by some eigenfunctions. And there are infinitely many of these eigenfunctions for interesting kernels. But that doesn't tell us what the space actually looks like. So to get a sense for what that space looks like, I'll now make a closer connection to statistical machine learning. And I mean, by now, actually, I realized that Matthias Hein is not actually doing much of this theory anymore. So if you want to hear more about it, maybe you have to prod him a bit in his feedback section in Moodle or so to do more on this. A first step for that is to realize that this Gaussian process regression that we're doing here comes under many other names as well. So maybe in some other lectures elsewhere in your previous life, you haven't heard about Gaussian process regression, but you might have heard about kernel-rich regression. Kernel-rich regression is the exact same thing as Gaussian process regression. I'll point out in a second. Who has heard of kernel-rich regression before? The people who've done a math class, I guess. OK. Who has heard of Wiener-Kolmogorov prediction? No, no one. Probably. Maybe one. Kriging. If you had people here from the geoscience community, Kriging might be the name that you might have heard about. Well, and you've heard from Matthias Hein about ordinary least squares, linear least squares, and so here you've realized that there's some connection. What is that connection precisely? Well, we can make this connection directly precise when we decide to instantiate the Gaussian process. So if we, for a moment, put aside this function-valued object, this lazy thing that needs to be instantiated, and decide which space we want to do the inference on. Let's say we choose the axis. Then the object we are computing is actually just a Gaussian distribution, as you know. Right? It's not a Gaussian process. It's a Gaussian probability density function that is defined over these finitely many function values. And it has this posterior mean and posterior covariance that we've now looked at many times. So I can just leave them there. So how should we think about these objects? Well, let's first focus our attention on the mean. Why? Because in statistical machine learning, the mean is all people care about. It's the point estimate. And this cool object quantifying the uncertainty often falls under the table. So let's first look at just at the mean. So the mean of a Gaussian is also the mode of a Gaussian, right? Because Gaussians are these bell-shaped things, and the mean is just in the middle, where the peak is. It's not generally true for probability distributions, but for Gaussians it's true. So we can also talk about the mean as the mode of this probability density function. Question? Or are you just stretching your arms? Okay. And that mode we can also describe as the minimum of minus that probability density function, or minimum minus the logarithm of the probability density function. We've now done that already, like 15 minutes before. So what is that probability density function as a function of the mean? What is the minimum of the logarithm of the probability density function as a like, where does that lie? Well, it lies at this term, which we can think of, I got confused for a second, as minimizing the negative logarithm of this expression up here, right? So we can sort of go back up instead of computing, reading off what this quantity is. We can also think about what we actually do, right? We write this probability density function, and we minimize its negative logarithm. So if you take the logarithm of this expression and you only care about quantities that involve f, then if you take the logarithm, first of all, this becomes a sum of log of this plus log of this minus log of this. There is no f in this expression, so it's just a constant, doesn't matter for maximization. So we get negative logarithm of this minus plus negative logarithm of this prior. And that's the expression we have down here. So, in other words, Gaussian regression, as I've already mentioned before, is the same as finding the least squares estimate under the data for f when regularized by a quadratic loss centered on the mean. So it's regularized least squares regression. And this is actually how this historically also came about. There is a historical debate about who invented these methods. The first one might actually have been this guy, Adrien-Marie Legendre, French mathematician. There is no known better image of him than this sketch. We just don't know what he actually looked like. There is apparently a painting of someone who was supposed to be Legendre, but it's a different Legendre. It's not this guy. There's only one sketch that was drawn by a satirist, like by one of his friends who was just a hobby painter, and he drew this during one session. So he must have been a bit of a character. And in 1805, he published a treatise on new methods for the determination of the orbits of the comets. And you can read this here in the original French. The important thing is, he says, here's this, the method which has to be the simplest, the most general among all of these, consists of minimizing the sum of the squares of the errors. And then we get an equation with unknown coefficients which we can solve to determine the orbit of polynomials. This method that I'm talking about, which Legendre call the method of least squares, has a great utility for all of physics and astronomy. And so therefore I do a derivation here in the back in the appendix. And then in 1877, Gauss did basically the same thing also for planets, well, like Himmelskörper, this time planets. And he writes in German, he ignores Legendre, maybe he knew of him, I don't know. But he says, yeah, we can do this. Like, if you want to know the trajectory of planets, then es ist von selbst klar, dass damit das Produkt ein größtes werden müsse. So that's exactly what I just did on the last slide, right? To find the mode of this probability distribution, that means that the negative logarithm of this has to become minimized, ein kleinstes, and therefore the most probable system of the values of the unknowns in these equations is the one which minimizes the square distances between the observations and the predicted function values. There it is, Gaussian process regression. And that's why we call it Gaussian process regression. and not Legendre process regression because, I don't know, he had a fancy picture of himself drawn and was like a fancy university professor, while Legendre maybe wasn't quite as good in the PR department. Okay, so this is least squares. It's this fundamental quantity that has been used in science ever since modern science has been a thing. I mean, this is like, I want to like, basically like just from Newton forward, right? So that's the connection. This method that we're using here is not some philosophical Bayesian invention that Kolmogorov came up with in the early 20th century. It's the exact same method. It's just interpreting it in a different way, as scientists have been using since, well, 1805 at least. So when we use this non-parametric extension of this mechanism, this kernel method, then how should we think about this object here? So when I instantiate the Gaussian process on a finite set of points, then I have a finite vector f here, right? And then I can write down an L2 norm of a finite vector, that's fine. But before I do that, before I instantiate this Gaussian process on X, this Gaussian process prior thing that we define that has this kernel in there that doesn't yet get called, what kind of object is this regularizer here? This is obviously important because this regularizer spans a space of hypotheses. So if you want to understand what kind of assumptions these models make, we have to understand what kind of space of functions this thing here spans. And to do that, here is my way of doing that. This is not the way you would find in these textbooks. It's actually sort of backwards from how the textbooks would do it, but it works from our Bayesian perspective a bit better. So let's say we have a data set like this. Here's this red curve. That's our posterior mean. We've now computed this a few times. I've now decided to use the square exponential kernel just to make the plot, but let's assume it's a general kernel, right? Then this object, this posterior mean that we are computing, it looks like this, right? So we've now had this a few times. So one way to look at this object is first to do what every good mathematician would do and get rid of the annoying bits, which is to say, let's just set the prior mean to 0, because then this prior mean business just drops out. So we can ignore this bit and ignore this bit. So now we have this kernel at the predict points, at our lint space where I make this red line plot, and all the training data x. So this is this. On the left-hand side, it's a function-valued object that I can instantiate wherever I want. And on the right-hand side, it's a finite object that takes the training data points in. And then I get this multiplied by a finite matrix and a finite vector. So vector times matrix is a lot of computation going on, but it's just going to be a vector. So let's give a name to this vector. Let's call it alpha. So what we've now seen is that we can write our posterior mean function as a finite sum over weights times a function of only one variable, namely this little x here. And on the right, that function is instantiated by the training points, xi. So now we can ask, what does this space look like that I can address in such a way? All posterior mean functions, no matter how I choose the kernel, and no matter what the data set is, will have this algebraic form. There will be a weighted sum of kernels. So the space of functions addressable in this way is the space of functions that look like this. What does that space look like? So first of all, let's give a name to that space. It's called H. There's going to be a reason why it's called H. It's nothing to do with my last name. So the space of possible posterior mean functions looks like this. So one first thing we can do is we could say, well, we want eventually to do something like least squares, which I pointed out on the previous slide, right? So we want to have a norm. Well, how do we get norms? Well, norms in math arise from inner products, right? A norm is always an inner product of something with itself. So how do we get an inner product? Well, let's define an inner product. I propose that we define an inner product between functions that come from this space, like this. So this notation with the angled brackets is just meant to be an inner product. So this is like your numpy dot inner of two functions. And I define that we're going to use this object for this. So remember that every such function has this form. So I can, in particular, write this down. right? So every function is identified by a vector of weights W. It has finite length, but unbounded finite length. Maybe even countably infinite length, but I can write down this sum. And so I have these W's, and I can put them together. And I also have all these xi's and xj's for the two functions, and so I can just put them into the kernel. That's my way of defining an inner product. So first of all, why am I putting why? Well, because this is actually an inner product. So let me show you that this is an inner product. Who has seen inner products in first-year undergraduate classes? A few. Oh, actually, more than half. Good. So you remember, of course, you all remember what an inner product is, right? Good interview question. So it's a function that is symmetric, a function of two inputs that is symmetric, right? The inner product of f and g is the same as g and f. You can clearly convince yourself that that's the case. It's also linear, bilinear actually, in both of its arguments. You can convince yourself that that's the case for real numbers, alpha and beta, and two functions. And it has the property, that's a little bit less obvious, that the inner product of f with itself, which we also call the norm, is always larger or equal than 0 and equal only if f is equal to 0. So I could ask you to do that proof for yourself. Maybe you can, it's a one-liner using this expression here, where you might want to realize that what we're building here is a matrix K XX, which is multiplied from the left and right with vectors W, and it's the same vector. Right? For if f, the left and right hand side is the same, so that's going to be a positive number because k is a positive definite function. Aha. Good. So this works. So therefore, these are the three properties that make an inner product. So now we have an inner product space. Inner product spaces are, there's a technicality that you may remember if you've had functional analysis. They're not quite yet all that interesting yet. They have sometimes a bit of they're called pre-Hilbert spaces. Maybe you've heard that term. To make them useful, we need to make sure that they are complete, so that all sequences in them converge. And that's a technicality. Just ignore it. It's possible. It's always possible. And then you can do that, and there's a unique way of doing the closure of these completions. And then that space is called a Hilbert space. So the space of posterior mean functions of a Gaussian process is a Hilbert space. So if you've heard that word before, now you have some connection. And that's also why it's called H for David Hilbert. And there is a very interesting property that this kernel has, which we can convince ourselves of. So we now have this inner product between functions in that space, right? So now we can look at a particularly interesting function, and that's the function where we set n to 1 and w1 to 1. So that's just the kernel, evaluated at any particular location x. That kernel has the interesting property, it's down here, that if we take any function from that space and take the inner product with the kernel, which is this like simplest possible function in that space, then by definition of the inner product, we get this object. You just plug it in from up here, right? We said there's only, j only goes from 1 to 1, and this one is just a 1, so this is just this sum. And then we can look at the definition of f, and we see, oh, but that's f, evaluated at x. So this is a bit like how the one matrix acts in normal finite dimensional vector spaces, right? You can take the matrix 1 and take the inner product with an arbitrary vector, and then the elements, the column, the rows of the one matrix reproduce the elements of the vector v. So therefore we say that the kernel has the interesting property that it reproduces this particular Hilbert space. It's not just any old Hilbert space. It's a Hilbert space that has this special object k which reproduces it. And therefore this thing is called a reproducing kernel Hilbert space, RKHS, which is a fancy term that used to be all over machine learning up until about 10 years ago. Here's the definition of reproducing kernel Hilbert spaces. So a reproducing kernel Hilbert space is a Hilbert space which has this special function k which reproduces it. It's literally just what we just did. That's it. Right? There's nothing new. And it turns out that there's a theorem by Aron, which says that RKHSs and kernels are actually uniquely identified by each other. Whenever you have a positive definite function, you also have an RKHS. And whenever you have an RKHS, you also have a positive definite, uniquely identified kernel by this. And this is actually, I mean, we've actually already just now we almost did the proof for this. I mean, I waved my hands around a lot, right? And there's a few technicalities, but that was the idea, right? The construction that I just made. And it turns out that that inner product, that norm that I just defined in the reproducing kernel Hilbert space, that is the norm we're minimizing as a regularizer for our kernel width estimate. So Gaussian process regression is kernel width regression. So it's regularized least squares regression, where we find functions in entire function spaces, infinite dimensional function spaces, by regularizing the finite dimensional empirical risk with a norm in a Hilbert space. Now, really, I feel this is something you should have learned in the statistical machine learning class, but I guess you haven't so far? No? No? Those of you who go to Matthias' side? I actually met him yesterday in the corridor, or on Tuesday, and I said, you're not doing RKHSs, right? And he said, there's so much else to do, not important anymore. And I said, no, it's still important. You have to, So please go back and ask him about RKHSs. It's a very important thing, because then I said, Matthias, I'm doing it in my class. Why are you doing RKHSs? And I said, well, because I want to point out what the posterior uncertainty of a Gaussian process is, actually, because it's connected to a worst case error in the RKHS. What? I didn't know. Okay. So let me show you something that even Matthias Hein didn't know. Very proud of this result. It's from this paper by Motonobu Kanagawa and others that I linked on above, which says that there is actually an interpretation for the posterior variance. And I've shown you this because I find this is the most direct connection between statistical machine learning and probabilistic machine learning there is. And it's in its technicality, it's a bit annoying, but when you get the gist of the statement in the end, it's a very deep result about why these two groups of people tend to disagree with each other about their analyses. And here is how it works. I'm going to give you a way to construct the object we call the posterior variance completely without talking about probability distributions. Okay? So if you don't like probabilities and if you think Bayesians are religious, then here's a functional analysis perspective on everything we've been doing in the past few weeks. So I've now constructed this space of functions called the RKHS, the reproducing kernel Hilbert space. And we can now talk about mean estimates being constructed by our kernel width regression algorithm, which is also a Gaussian process regression algorithm, mean functions. And you could ask, how bad are those mean estimates? How far can they be from the true function? Well, to make such a statement, you have to make an assumption about the true function. If you are a Bayesian, you would say, oh, that true function is probably a draw from some probability distribution. But we're not allowed to do that because we're doing a non-Bayesian analysis. So what we're going to say is, we're going to say the function actually comes from the RKHS. It's an infinite dimensional space, so that's maybe not a particularly strong assumption. And I've heard my colleagues say that actually, not just Matthias, not Matthias Hein, he wouldn't do that. But other colleagues will be like, it's going to be from the RKHS. And that's a weak assumption. Okay. So let's assume it's from the RKHS and it has bounded norm, bounded by a constant. I mean, you might as well make the constant 1, but you can also say by an arbitrary constant. So that's the thing here. And let's look for the worst possible error we could make. So the supremum of the square distance between function values at the predictive mean, at our point estimate, and the true function which we don't know. So here is how the proof works. First, we plug in, or how the construction works. First, we plug in the definition of what the posterior mean is from a few slides ago. Let's say we've made observations without noise. There's no regularizer. It makes the analysis a bit easier. So, sorry, not no regularizer. There's no sigma is 0, right? So that means the Gram matrix here is just kxx inverse. Makes the entire thing a bit easier. Also works with noise, but then it's technically more complicated. You can find the full derivation in this paper. So that's the definition of the posterior mean. Okay, who is still following? Uh-oh. Oh, it's a bit of nodding, okay? So far I've plugged, this is going to be, every single step will be feasible, and then the whole thing will be a big step, right? Just like often in math. So just bear with me one step after the other. So I'm making this, like this object is of interest to me. I want to know how bad I could possibly be with my point estimate, how much I can trust my posterior mean, right? So for that, I look at what is the posterior mean of my Gaussian process regressor, my kernel-rich regressor. I write in the definition. It's just a weighted sum of kernels, weighted by the Gram matrix inverse times the observation, right, y. And y is f of xi. I'm assuming I have actually evaluated the function without noise. Here I haven't changed anything yet, still minus fx squared. Now I use the fact that I can write every function value in the RKHS as an inner product with the kernel. That's the reproducing property. That's this beautiful, cool ability of the kernel. So I'm going to turn these round brackets into square brackets, inner products with the kernel, by taking all, wherever there is an f, and replacing the f with an inner product with the kernel at the point x or xi that I want to evaluate at. Okay, so this is this reproducing property. Everything else stays the same. Now, what I have here is an inner product between one function and another function. And that other function is the thing that I want to find the worst case for. So I want to find the worst possible function f in the RKHS of bounded norm, which has this such that this number here gets as large as possible. Right? That's a real number. I want to make it as large as possible. The way to do that with inner product is always the same trick. It's called the Cauchy-Schwarz inequality. Who has heard of Cauchy-Schwarz? Everyone has heard of Cauchy-Schwarz. Very good. Good. So it's this inequality, right? And you can convince yourself that you can maximize this expression by setting a equal to b. And whenever you do that, it's always a bit in your head, you go like, what? How does this work? You need to just think about it for 3 minutes, and then you realize why. Okay? Basically, there's two different ways of reading the inequality that shows that the thing that maximizes this expression is a equal to b. So we set f equal to this expression. And then you get an inner product between this expression with itself squared. That's just the norm squared of that expression. Okay? So now we have something in here that involves kernels again. And now we use the reproducing property again, because we get an inner product between kernels with itself, right? So the norm is an inner product of something with itself. So wherever there is a kernel being inner producted with itself, the open bit of the kernel goes, it vanishes, and out comes kernel evaluations of the function, reproducing kernel property again. Okay, and now we're left with a finite dimensional object. It's just a bunch of numbers, and the rest is just algebra. We're just moving things around. Or we look up what is W again, or W is up here, so we just plug it back in. We see that some matrices cancel. It's just dealing with indices, and we're left with an expression that is the posterior variance. So what we've just seen is the following statement. If you're a Bayesian and you're building Gaussian process regression model with zero mean and noise-free observations y of some function using a kernel k, you'll get a posterior mean estimate, which we've constructed with our condition method. And that posterior mean estimate has some form. And then if you're a Bayesian, you could ask, well, how uncertain am I about that estimate? Well, that's the posterior covariance, right? I've constructed that a few times. So I can draw from this process. I can write down this posterior covariance object. And I will talk about that as what? As my expected square distance between function values. When I made these plots with these sausage-like regions around the mean, right? So literally, I mean, they're still there, right? So these plots, these dashed lines, they are my expected error. They're the square root of the expected square error. So I expect that the true function is about this far away. But I can think about these dashed lines in a completely different way from a statistical analysis perspective and say, assuming that the correct function comes from this reproducing kernel Hilbert space spanned by this kernel, reproduced by this kernel, the worst possible error I could make, assuming that the true function has bounded norm, is this dashed line. So if you've ever heard from someone, I don't know whom, I don't want to name any names, that statistical machine learning is the sort of pessimistic, worst case type of analysis, while the Bayesian analysis is the more optimistic kind of expected value analysis, In this case, they're exactly the same. And now you can wonder, and this is the statement that I want to leave you with for your lunch. How can it be that one person's worst case estimate is someone else's expected error estimate? However, the person who thinks about this as a worst case estimate thinks of themselves as a pessimist and thinks of the other guy as an optimist, even though they're assuming that they're going to make that error. Isn't that backwards? It is. And maybe that's why you don't hear about this in the statistical machine learning class. I'll save the other bits because they're just one short thing to show. I'm going to stop here and use the last 2 minutes to summarize, just briefly, and then I can see if I can answer questions. The first half of today's lecture was about learning hyperparameters for Gaussian process models. We found out that we can basically reuse the Bayesian framework to also learn parameters of a model, but then the computational complexity rises when we compute marginal likelihoods. And we are not able to compute the full posterior anymore. Instead, we just use the numerical optimizer to find the mode of the distribution. Then we realized that that mode wasn't quite a convincing point estimate, so we used the Hessian around the mode to get a sense of how confident we are in that mode estimate. And then in the second half of today's lecture, we did something slightly different related to the same model class. We started to wonder what kind of analysis they actually correspond to. What kind of spaces are we dealing with here? What kind of objects are being created? Well, we looked at the posterior mean, the point estimate returned by these objects, and we found that those means lie in an interesting space called the RKHS, which has a deep interpretation in classic statistical machine learning analysis, statistical learning theory, and discovered as my punchline at the end that the error estimate produced by this probabilistic method that we've been working with for the last few weeks, actually, even though it's for us an expected error estimate, can also be interpreted as a worst case estimate in the space of mean functions, the RKHS. And if you're wondering about the connection between these two and this claim that I just made, maybe to help you on your mental journey of how these two things can be true at the same time, the trick behind the scenes is that the hypotheses classes are different. Or to put it more concretely, samples from a Gaussian process are actually not in the reproducing kernel Hilbert space. So when the Bayesian says, I'm assuming that the true function comes from a Gaussian process, they actually talk about a different space of functions than when a frequentist says, I'm doing kernel-rich regression. And because that kernel-rich regression space is narrower and more compact, this group of people makes a stronger set of assumptions. And they very quickly, they sort of easily can go under the radar. And then it's possible to make worst-case statements that are actually expected error statements in the probabilistic sense. If you want to find out what space the samples from a Gaussian process come from, you have to wait until next Wednesday, when Marvin does, Thursday in 2 weeks, when Marvin does a tutorial, he can tell you about it, and he can tell you all about it. So ask him, and he'll let you know. Please give feedback, and then next Tuesday, we're back with time series, a new model class, problem class.